This video is part of the Commercial Building Electrical Design series. We're continuing our look at power distribution design. We've been looking at branch circuits, and now we want to talk about conduit sizing. So again, as we've done in the other videos, just kind of giving a snapshot of where we are in the process here. We've talked about delivery systems, materials, and we're trying to wrap up our branch circuit sizing, looking at different types of branch circuits, ground wires, and now we're talking about how to size the conduit. So we're almost complete with our analysis of branch circuit sizing. We've seen how to size the conductors and breaker depending on the load type, and we now understand the relationship, hopefully, between the grounded and grounding conductors and how to use and size them. All that's left now is to put all this together in a conduit, and then we'll be done. But what size conduit? Well, that's what we're going to look at next. We're going to see what's involved with sizing our conduit for our branch circuit. So remember that one of the main things we're trying to do in all of this is manage the heat produced by the flow of the electrical current. So as you can imagine, as the current flows through the conductors in a conduit, this could present a significant opportunity to have heat build up as the conductors continue to produce heat, and this heat is trapped inside the conduit. Because of this, there are some safeguards put in place by the National Electrical Code that we must adhere to. So we now want to take a look at these guidelines and use this to help us correctly size our conduit. So in order to provide ample space to allow the heat to flow through and out of the conduit, the National Electrical Code has a restriction on how much of the cross-sectional area can be used in a conduit, that is, by the conductors. So this requirement is found in NEC Table 1 in Chapter 9, as seen below. So here is that table, and as you can see here, that if you have one conductor in a conduit, it can take up 53% of the cross-sectional area. If you have two conductors, it can take up 31% of the cross-sectional area. But anything over two conductors, you can only use 40%. And this is where we live most of the time, right? Because we usually have at least a ground, a neutral, and a phase conductor. So that being the case, we almost always use the 40% fill number. So again, from this we can see that for most cases the maximum cross-sectional area that we'll be using in circuits that we design, our branch circuits, is 40%. So with this knowledge, we can now proceed in this process by calculating the total cross-sectional area required by our conductors. To do this, we need to determine how many of each size conductor we need in our circuit and look up the corresponding areas from National Electrical Code Table 5 in Chapter 9, and we'll look at that on the next slide. So here is that table. It's actually just a part of it. It's multiple tables. We're looking at the table for THHN, THWN, which we've talked about before, is probably the most common wire we will see. But you can see here, it goes down the first column by size, and here it gives the approximate diameter for each of these in millimeters and inches, and then the approximate area in millimeters squared and inches squared. So at least in the United States, we usually live in this column down here. This will give us the cross-sectional area for each conductor. So once we have the required cross-sectional area required for all of our conductors, we can now divide this value by 40% to give us the minimum required cross-sectional area of our conduit. Now that we have this value, we can go to the NEC Table 4 in Chapter 9 and find the table for the type of conduit we plan on using. We then use this table to find the conduit that has the required cross-sectional area for the given wires. Once this is located, we can determine what the minimum conduit size is for our circuit. Of course, we can use larger if we want, but we can't go smaller. Table 4 sections for EMT conduit and ridging conduit are shown on the next slide. So let's take a look at that. So again, here are some sections from Table 4, Chapter 9 of the National Electrical Code, and you can see It's referencing Article 358, which is EMT conduit, and Article 344, which is rigid metal conduit. And here we have the trade sizes on the left. It also gives the metric equivalent to what these are, but we usually work in the inch metrics here. So they give quite a bit of information here for you, and they've actually done some calculating for you. So they give you here the nominal internal diameter for each of the trade sizes of conduit for each type. They give the total area, so this is the total cross-sectional area. Then they give 60%, did that calculation for you. And then they do the three calculations based on the table we saw before for 1 wire, 2 wires, and over 2 wires. So again, we stay in this column. So here they've actually done the calculation for you. They say this is, well, the total, let's take ½ inch for example. So the total area is 0.304. The only usable area is 0.122. So we can only fill up this much of the cross-sectional area. Even though there's 0.304 available, we can only use up 0.122 square inches with our wire, our conductors. And again, same thing for rigid. So again, they've done the calculation for you. So you could take this and multiply it by 0.4 if you want, but again, they've done the work for you because they know that's what you're actually probably looking for. One last issue that is worth noting here is that not only is there a limit on the cross-sectional area that can be used in a conduit, but there is also a limit as to the total number of current carrying conductors in a conduit, because it's the current carrying conductors that will produce the heat, right? So this is, at least in a sense, this is the case. It should seem obvious that as we increase the number of current carrying conductors, that the rate of heat rise should also proportionately increase. So this being the case, in the presence of this increasing heat, or heat producers, the conductors increase the risk of incurring damage to their insulation. So to remedy this, the National Electrical Code requires that as the conductor count is increased, the rated ampacity of the conductors must decrease to compensate for this additional source of heat. This is shown in the NEC table 310.15b2a on the next slide. So we refer to this as conductor derating. So sometimes we have to derate our conductors if we meet these conditions. So let's look at the table. So here's table 310.15b2a, and again, these are adjustment factors. So if we have 0 to 3, or 1 to 3, maybe I should say, current carrying conductors, then we can use 100% of the value from the tables in 310.16. So our normal ampacity tables. Once we get to that fourth current carrying conductor, if we go from 4 to 6, we can only use 80% of the rated capacity. If we go to 7 to 9, we can only use 70% of the capacity. So on and so forth, up to 41 conductors, which you don't usually see that in a conduit. Where you might see that is in a wireway. But you know, if you have that many current carrying conductors, you can see you're really having to derate that wire. So you're really not helping yourself by trying to stuff more wire in a conduit, at least from the National Electrical Code standpoint. So again, for 3 current carrying conductors or less, the conductors can be used at 100% of the ratings. Otherwise, their ampacity rating must be derated as shown in the table above. So this means that if we have 3 or fewer current carrying conductors, we're fine to use the tables as is. So now this raises a very interesting question. If we are feeding a 3-phase panel, we should have 3 phase conductors, 1 neutral conductor, and 1 ground conductor, or grounding conductor, for a total of 5 conductors in our conduit. So the first question is, what's considered a current carrying conductor? And the second question is, do we have to derate our conductors in this case? Why or why not? So hopefully it should be obvious the phase conductors are going to be current carrying, right? If we have any load at all, they should be carrying current. But the big question is going to be, what about this neutral and this ground wire? So taking question 1, again, we know from the ground conversation, for the grounding video, a couple of videos back or so, that under normal circumstances, the grounding conductor should not be conducting any current. Therefore, it does not have to be counted. All right, so of our 5, the ground is not conducted. We don't consider that a current carrying conductor. So we go from 5 to 4, but that 4 still puts us in the 80% column in that previous table. So as I stated before, we also have 3 phase loads that if the loads are balanced, then the current in the neutral should be minimum or 0. Most inspectors and plan reviewers do not require the neutral to be counted, as it is expected that there should be little or no current flowing in this conductor under normal conditions. We'll talk about this later, but as you're doing panel design, many reviewers are going to require you to have it balanced within 10% across all 3 phases. So as you can imagine, if they are truly balanced, even with some mismatch, the current flow in the neutral should be very, very low. Probably not 0, but minimal at best. So now we need to go to question 2. Before we go to question 2, let's just review a little bit. So we have 3 phase conductors, which we're saying are current carrying. We're saying the ground is not current carrying, and we're going to say we're doing our design right and balancing our loads well so that our neutral doesn't have to be considered current carrying. So now we got 3 for sure, 2 probably not. So now to the second question, do we have to derate our conductors in this case? Why or why not? Well, since we do not have to count the grounding conductor and probably not the grounded or neutral conductor, this reduces our total number of current carrying conductors from 5 to 3, which is below the threshold of requiring derating of the conductors. So in summary, grounding and grounded conductors are counted when figuring cross-sectional area, but not generally counted when counting current carrying conductors in 3-phase circuits. The neutral should be counted in a single-phase circuit. So if you've got a single-phase circuit, we do count the neutral. 3-phase circuits, we generally do not count the conductor. So one interesting case that pops up many times, though, is modular furniture. So modular furniture usually can come in 3-circuit, but it also comes in 4 circuits furniture. So you have to supply 4 circuits to it. So, many times depending on how you're going to run your conductors to this location, it could require you to derate your conductors, which oftentimes we have to. So we'll upsize it to number 10, and that usually takes care of things for that. But again, this can cause a lot of confusion in the industries. A lot of times people think when they run a 3-phase 4-wire circuit that they have to derate the conductors. This is generally not the case because we don't have to count the neutral in most cases as a current carrying conductor. So let's look at an example. We want to consider a 3-phase branch circuit that is being fed with a 100-amp breaker using 4 number 3. We're going to use the dual rated THH, THWN. So that means there's 3 hots and 1 neutral. That's why there's 4 of them. And we're asked to complete this branch circuit specification by sizing the grounding wire and the conduit, assuming we're using rigid metallic conduit. So since this is not an incoming service, we know that we can size the grounding conductor using table 250-122 from the code, from the NEC, and the fact that the circuit can be fed with a 100-amp circuit breaker. So that's all the information we need to size the ground. So let's look that value up now. So here's our table 250-122. Again, we know that we have a 100-amp breaker. So we simply just read across there, and this gives us our ground wire size, or equipment ground size, and it should be number 8 minimum. So we now have that information. We put it all together, and now we have our 4 number 3s, which we were given. We've added our 1 number 8, and we usually designate this by putting a little G by it or something like that to let people know that that's our ground wire. So we now need to calculate the total cross-sectional area of all of the conductors that will be in the conduit. To do this, we need to look up the cross-sectional area for number 3 and for number 8, and we'll do that as follows. So here we go back to table 5 in chapter 9 of the National Electrical Code, and we see we're using our THHN, THWN because that was given to us. That's the type of conductors we'll use, and we'll assume that's what we'll use for the ground. It'll be a green colored insulation. So using the table, we know that we will be using number 3, and we know that we'll be using number 8 for the ground. So to get the cross-sectional area for a single instance of these wires, you see we just read across the table, so it'll be 0.0973 for the number 3 and 0.0366 for number 8. So back to our example from the table, we see that number 3 is 0.0973 and number 8 is 0.0366. So we can use this now to calculate the total area as follows. Since there's 4 of the number 3 phase, 1 neutral, we'll say 4 times 0.0973, so that gives us a total cross-sectional area of 0.3892. Then for the number 8, there's only 1 of those, so we just bring that straight across. Then we add those together, so the total cross-sectional area used by our conductors is 0.4258, a little under half an inch squared. So we take this information and we're going to use this to determine the minimum area for the conduit we need to take the total area of the wire above, and we can do that by dividing it by 40%, because it has to be 40% or less of the conduit. So the minimum conduit area, we'll take our 0.4258, divide it by 0.4 for 40%, and so that's 1.0645. So now we use this number to go back to table 4 of the National Electrical Code for rigid metallic conduit, and this will help us to find our minimum size conduit. So again, here's our table for rigid metallic conduit, and we know that rigid RMC. So we know our total area. We find it in this column, and so we go down and we find where we're above that minimum, the first point where we get above the minimum, and that's when we get to 1.526. And so then we read it over to the trade size, so that's going to be 1.25 inches. So that's the minimum trade size conduit to be code compliant for this branch circuit. So from this, again, we can see that the minimum size conduit required for this circuit using rigid metallic conduit or rigid metal conduit is 1.25 inches. So we could have just used the total area of the wire and the 40% column, and we would have obtained the same results. So again, here, rigid metallic conduit, instead of using this column for the total area, we could have gone to this column and gone down and found the 0.610. And of course, this is before we divide the total conductor area by 0.4. Again, here we just use the total conductor area. And here we see that the first time we get above that minimum is here. Again, read it back across, and it gives us the same result, 1.25 inches. So here, either way, we now have our branch circuit fully defined as follows. And so this is the way we would note it on our plans typically. It's 4 number 3, 1 number 8 ground with 1.25 inches C for conduit. And so now we're done sizing our branch circuit. This is the total information we need to supply on our plans.